One of the main uses of IR vision is to locate parts or features and communicate the location of those to the robot. The robot is then able to offset its motion to compensate for the change in location. Setting up frames is an essential part of that process. In this presentation, we will learn about the different frames and how to set them up for IR vision. Tool frames are critical for any robot motion, as you learned in MEC251. For the lab, you'll be setting a tool frame for the gripper and camera end of arm tool. To do this, you'll want to use the 6-point XZ method. This tends to be the preferred method for such a tool. This means that you'll be defining the positive directions for both the X and the Z axes. For when setting up these axes in your lab, you're going to want to make the X and the Z axis in the same direction as the world frame. Let me show you what that will look like. So here in RoboGuide, I currently have the robot moving in the world frame. You can see as the Z axis in the positive direction goes up and the X positive direction moves forward. If I switch this to the tool that I've taught, which is tool 2, which I'm currently in, and let me shift my coordinate to tool. Past it. The tool frame is in the same orientation, so I've got my positive Z going up and my positive X going forward. If we were just to do this with the normal 3-point method, our positive Z would actually be pointing downward. And so for this example, I don't want that. I want it pointing up. So for your lab 4, make sure that you have that oriented very similar as you would for the world axes or for the world frame. Okay, another frame crucial to the IR vision is the application frame, sometimes also called the offset frame. This is just a user frame where the work happens or where the parts are located. In the example here, the application frame, shown in pink, is the table near where the conrod sits. The application frame setup is just like any other user frame. The 3-point method is the most common way to set up the application frame. If needed, you can review the user frame video presentation from MEC251, and I've made sure to include a link to that video on the lab instruction sheet. The final frame we'll discuss for IR vision is the calibration grid frame. This is a user frame that is set up at the origin of the calibration grid and aligned with the calibration grid's X and Y axes. It is best to teach this frame using the 4-point method. The calibration grid is a specific dot pattern that the IR vision can recognize and use to determine the pixel size to distance relationship. The dots are arranged in a specific spacing with an orientation that defines the X and Y axis direction. So you see here in this image, we've got 3 different types of calibration grids available. We have a 7.5 millimeter, which tends to be the smallest, a 15 millimeter spacing, and a 30 millimeter grid spacing. The spacing refers to the distance between the individual dots. The calibration grid's X and Y direction is identified by the 4 large dots in the center of the grid. The X-axis is identified by the 3 dots in a row, and the Y-axis is identified by the 2 dots in a row, seen here by this red line. Where the 2 axes intersect is known as the origin of our calibration grid. To teach the calibration grid frame, we select the user frame from the user frames list that we want to use. The best way to teach the calibration grid frame is with the 4-point method. With the way the calibration grid is oriented on the screen, the orient origin is in the top left-hand corner, shown here by this dot, and you can see the small white dot inside the black dot. The X direction is extended downwards from this orient origin, okay, following the 3 larger dots, or the same direction as those 3 large dots. And then the Y direction, we can go to either point at the other end of the calibration grid, opposite of the orient origin or opposite of the X direction point. So the orient origin and the X and Y direction define the user frame surface or plane. However, for the calibration grid frame, the user frame needs to be placed in the middle of the calibration grid. Using the fourth point, the system origin, shifts the user frame from the orient origin point to a desired location. In this case, it's the center of the calibration grid. You might ask, why not just use a 3-point and teach it from the center of the calibration grid? By selecting the orient origin in the corner of the grid, a longer X and Y axis direction are able to be taught. This improves the accuracy of the calibration. Okay, now let's step to our RoboGuide example and look at both of the application user frame and the calibration grid frame. Right here I've got my work cell in RoboGuide, and I'm going to show you first the application frame and where it resides. So the application frame shown here in pink is just my tabletop. I've elected to pick my origin point here in the bottom, I guess, right-hand corner of the table if you're standing behind the robot. And it was really arbitrary, and you're welcome to pick an arbitrary point as well, as long as it matches the table, the top of the table. Okay, for my calibration grid, if I zoom down, shown here in this blue, by this blue square, you can see where it is oriented here in the center. The origin is oriented here in the center of the calibration grid. So when originally taught, I'm using this corner as my orient origin, this dot here as my x-axis point, or direction point, and then in this particular case, I use this back dot here as my y-positive direction point. However, either point would work. Okay, now let's talk about our 2D calibration. The 2D calibration is the way in which the digital image from the camera is related to the physical environment. So here in our IR Vision setup, I've got my calibration or my camera setup application currently open. So in our previous labs, we had a lab where we set up our camera, and we'll have to do that again for this work cell. Very similar to what we did before. But now we are going to move on to the next series of steps, which is setting up the 2D calibration. So going to frame 2, titled Calibration Setup. Over here we have the robot to be offset, which we've already selected, so it continues to be this robot. And then we have the application frame, which I set up as the user frame 1, this labeled tabletop. Now I could have just used a world frame if that was the frame that I decided to use for all my the points that were taught around picking up the part. However, for this example, I'm going to keep that as a user frame 1, defining the top of the table. The grid spacing for my calibration grid is 7.5 millimeters, so this is the smallest of the calibration grids. And here the robot held calibration grid. This is if we were using a robot to hold on to the calibration grid, most likely using a fixed camera or a separate robot with the camera. But in this case, our calibration grid is on the tabletop, so we can select no for that. And then setting the fixture position method, we're going to use the frame. Okay, once we've got that set up, we can go to the fixture position setting. And here it's going to ask us what is the calibration grid frame that we're going to use. And I have mine labeled as user frame 2. And then we're going to go ahead and set the fixture position. Now this is going to create the relationship between the calibration grid and the application frame. So the two frames, the calibration grid user frame and the application user frame. And once we've got that, we can move on to the fourth frame, which is for the calibration. And you see here under projection, we have our choice between perspective and orthogonal. So let's talk about what those mean. Okay, the perspective view is any normal lens. The part that we're looking at, especially if it has any height to it, will have a distorted image as the part moves towards the outer edges of the field of view. So you see here with this part, it has some height to it, and as it extends out here to the outer boundary of the field of view, we're going to see a little bit more distortion as a result of that lens. Orthogonal doesn't distort the image regardless of the part's height or position, but it requires a special lens called a telecentric lens. These lenses are quite large and expensive, so they are not readily used unless required by the application. It is worth noting that while a normal lens will always have a perspective view, meaning the image will be somewhat distorted, the distortion only really causes us issues with taller parts. If we have a part that is relatively thin or not very tall, we can use an orthogonal projection setting in our calibration setup instead of using a perspective. However, if the part is somewhat tall, the issues with the perspective lens has mostly to do with relatively taller parts. Here we see a part that is somewhat tall relative to the field of view. When the part shown is close to being directly under the camera, its centers between the top and bottom are aligned, and the software can easily communicate its positional offset. However, as the part moves towards the edge of the field of view, the center position between the top and the bottom are misaligned. If not compensated, the software, when calculating the positional offset, would project the center of the top of the part to the work plane underneath at the bottom of the part. This would cause a false positional offset and could mean the robot damaging the part or the part damaging the robot. Either way, it's not a desired result. So we have three ways in which we can compensate for a perspective view. I'm going to cover these, the first and the third view, or the third method of compensation, as they tend to be the most common. In the two-plane approach, we're going to set up two different planes. The first plane is the camera's normal position as it's looking at the calibration grid. The second plane, the camera is moved at least 100 millimeters either closer to the calibration grid, as shown in this example, or further away from the calibration grid. And it's moved along an axis that's perpendicular to the calibration grid. So let's look in RoboGuide and see how this would work. So here I've got in my calibration grid, I'm going to go ahead and select the number of planes that I'm going to use as 2. This defines this method as a two-plane method for the perspective view. The camera distance will be automatically calculated, and I'm going to go ahead and use this as my first plane, so I'll go ahead and find the plane. Now I can take the box view and draw that in around the dots that I want to recognize as part of the calibration grid. So this is very similar to what we did in the GPM locator of our last lab. So then I say OK. And now I need to find the second plane, but before I do that, I'm going to go back to my robot and move it 100 millimeters further away. So I've set up my grid position robot program or motion program to define those 2 points. So my first point here is point 1, and then I entered in a pause so that even if I'm continuously moving the program, it'll pause here before moving to the second position, which is above, moves the robot at least 100 millimeters above the calibration grid. So now if I just go ahead and hit shift and forward, now my robot has moved up above it's the original position, and so now I can use this as my second plane. Just as a side note, if you decide you would like to create a pause in your program, you go to instruction, and then under your program control, you'll see here a pause instruction that you can use. Okay, so going back to my IR vision, now I can do another snap, and you see that the calibration grid got a lot smaller. So now I'm going to go ahead and find my second plane, and I'll go ahead and drag my box, my view box, just so that I'm outside of those dots, and select OK. And now I have my second plane, my first and second plane both taught. Now I can go to my calibration points, and this is going to give me the error for each of those points. Like I said, the grid of a calibration grid is a specific pattern that the robot is able to recognize. And as a result, it can determine the error associated with finding each of those points. So here I've got the error associated with those with each of these points that are numbered, and I can select between different frames, giving me the error between each of those frames. And if I click on the error tab or column heading, it'll sort this either in ascending or descending order. So right now I've got it in descending order with the highest error value shown first. So typically we're not too concerned with it unless this gets into a value above 1. And what you typically find is that edges or our errors tend to be towards the outer edge of our calibration grid, where the distortion from the perspective lens tends to be the greatest. If we wanted, we could highlight one of these and then say delete, and then that would remove that from the calibration results and calibration calculation. If we're happy with everything there, then we can go now to the calibration result. And some of the important things that we'll want to look here is, one, it'll give us our focal distance of our lens. And with this particular lens, we know that's at a 12 millimeters. So this calculated that accurately. So we're spot on there. Our standoff distance is the other one that we would want to look at and see if this makes sense. Does this look to be the standoff position from our plane 1 above our application frame? And then also here, it gives us, similar to what we did in the vision inspection process, this also gives us a scale of the calibration grid, or the pixels, 2 millimeters. So here we're getting the physical representation of each pixel size, or of each pixel. Hey, if we're happy with everything there, then we would just go ahead and select Save. And so now we have our 2D calibration complete, and we would be ready to move on to setting up our inspection or our vision 2D process. Our last method that we're going to talk about in compensating for the distortion of the perspective lens is to manually enter the focal distance of the lens. The software uses this information to determine the distortion of the lens to the image. If you remember in previous discussions, the focal length is the distance from the lens of our camera to the image sensor. So the lens that we currently have on RoboGuide, installed on RoboGuide, is a 12 millimeter focal length. So let's jump back to RoboGuide and see how this would work. So now I'm going to my 4th frame for the calibration. I'm going to leave the number of planes as 1, my projection as perspective, and then I'm going to change this camera distance to override the focal distance. Now the focal distance for this camera is 12 millimeters. So if that was registering as something else, I'll just type in 12 millimeters there and then find my first plane. Similar to before, we just take our view box, and I'm going to size that just over so it encompasses the calibration dots. And now as it calibrates that, it comes up with a message that says the calculated standoff distance is 392.5 millimeters. So that gives us an indication that that we're on target with our calibration. I would go here to our calibration points. Since we just have the one plane, we can't really select any other planes here, so it's just showing us that first plane and the error associated with that. So I'm going to sort my data by descending order for the error, and looking at my error, pretty small so nothing to be concerned about there. Okay, and then look at my calibration result. Again, standoff distance looks fine. My scale is very similar to what I had before, 0.173 millimeters per pixel, so I'm happy with that. So we can go ahead and select Save, and now we have our calibration ready for the next step.